Hello everyone, and welcome back to a discussion on the introduction to parametric curves. During the in-class portion of this discussion, we introduced the notion of the parametrization of a given curve. We noted that this is a unique, interesting way to describe and talk about the functions, quote unquote, that generate graphs that fail the vertical line test. While we were in class, we talked about a variety of examples. In particular, we took a look at some examples involving parabolas, and we looked at a couple of examples involving circles. But primarily, we just talked about building a table of values and eliminating the parameter. In this companion video, I'd like to look at some additional examples in order to accentuate some of the not so obvious, more subtle attributes of parametric curves. So the first example I'd like to take a look at, so maybe we'll title this, we'll say more examples with parametric curves. So one thing that I tried to allude to yesterday, but I think is worth focusing on, is the fact that a parametric curve is allowed to copy on top of itself. So that's a quick note that we're going to make here, is that parametric curves, because they're allowed to fail the vertical line test, parametric curves can trace on top of itself. And this is something that a normal function has the complete inability to do. So I think one of the classic example of this phenomenon is the circle. So for example, what if I considered the parametric curve given by the equations, say, we're going to go cosine of t, sine of t, but here I'm going to let t run somewhere between 0 and, say, 4 pi. What we saw yesterday was that from 0 to 2 pi, that is half of this parameter's domain, this parametric curve traced out a unit circle in the counterclockwise manner. So the whole point here is that if I am going to use maybe green here, is that as long as t is running between 0 and 2 pi, then I'm going to start off at 1 here, and I'm going to move around in a counterclockwise manner and get back to where I started. And the minute that t enters between 2 pi and 4 pi, and it goes around that extra little bit, my parametric curve is literally tracing out the exact same thing all over again. And so what that means is that from 0 to 4 pi here, this is actually tracing out the unit circle in the anti-clockwise direction twice. And so there is a little bit of trigonometry running in the background. We know, for example, that sine and cosine each have a period of 2 pi, and therefore if I force their inputs to range all the way to 4 pi, I know that's giving me 2 iterations of the period, and hence we get 2 copies of this circle layered on top of itself. This immediately gives rise to other ways that we can replicate circles on top of itself. It seems to be linked to the period of sine and cosine here. And we know that one way to induce 2 periods worth of the curve is to stretch out the domain from, say, 2 pi to 4 pi. Or, of course, if we wanted to have 3 copies, I'd stretch out to 6 pi. But the other way to do that is to keep your window for your parameter from 0 to 2 pi, but instead force your function to speed up. So what do I mean by that? So I guess maybe one, yeah. So we'll take a look at that option as well. So and this I alluded to yesterday, I think as well. Another option we could get, c of x y. This is going to be again cosine, but now it's going to be say 2t, and sine of 2t. And here I'm going to let t stick to the normal 0 to 2 pi interval. And again, I'll highlight the main point here is that from 0 to 4 pi up here, sine and cosine have 2 periods. And the whole point here is that cosine of 2t and sine of 2t, individually, these have a period of 2 pi over 2, which is just pi. Which means from 0 to 2 pi, again, sine of 2t and cosine of 2t, we witness there are 2 instances of pi from 0 to 2 pi. So again, sine of 2t, cosine of 2t have 2 periods. So what that means is that the picture is going to look much the same, but with some slight difference. So if I'm going to steal this, it's going to be the exact same picture that I'm looking at. However, the parameters are different. So the picture is identical, but we get the first circle, the green circle, from 0 to pi, and we get the orange circle from pi to 2 pi. So the difference between these two examples is that, yes, the picture itself looks identical. However, the parametric curves look super different, and the domain for the parameter is different as well. So this again goes to show that just the picture is completely insufficient to fully characterize what's happening here. I might also note here that I also failed to put directions on my pictures. These are indeed counterclockwise drawings. So this is an example of two parametric curves that are going at different speeds. This parametric curve is going from 0 to 4 pi. That's a long time, and it's slowly just tracing out 2 circles. The second one is going in half the time, but it traces out the same exact 2 circles, so that has to go super fast. And as I increase my constant in front of here, you'll recall from trigonometric theory that that's going to increase or decrease the period and increase the number of periods that are present from 0 to 2 pi. If we did want to trace out, say, or change the direction, another example of that is to take a look at c of xy, but instead we're going to swap out sine for the first coordinate and cosine for the second coordinate. And let's make this go, say, from t goes from 0 to, say, 3 pi over 2. This is going to be a function that starts off at 1, but now it's going to move in the anti-clockwise direction 3 pi over 2, which puts us right here. Ooh, don't do that. In the clockwise direction. And so in this case, the initial point and the terminal point are different. Now, of course, I could have put some period changes in here as well and sped this up a little bit. For example, maybe I'll take a look at that. I'm going to take this exact same problem, copy, and I am going to instead induce some sort of a period change. Let's put a 2t in here for the exact same period. What that means is it's going to trace out this picture after only going through half the period. So what that means, for example, and this is where you have to start disassociating the parameter with the point on the curve. Because, for example, this point is the xy coordinate 0, 1. However, if the xy coordinate is 0, 1, then the t parameter that we're looking at there, in this case, is going to be 3 pi over 4. You can verify, for example, if I take 3 pi over 4, I plug it in here, I'm going to get 3 pi over 2, and sine of 3 pi over 2 is, of course, a 1. So this is not occurring at the 3 pi over 4 direction. The parameter is not being graphed here. It's only the xy coordinates that we have here. And then so what that means is that the blue curve that we have here, the blue curve is exactly what's happening for t between 3 pi over 4 and 0. And then if we wanted to continue the curve, the green curve would be going from 3 pi over 4 to 3 pi over 2. But again, we're not graphing those angles. It's just this is the parameter that we build over here on the left column, and then we trace out what those points are on the right. And that's going to build another copy of the curve, and that's going to end right here. Again, in the clockwise direction. So the total curve is the curve that starts here, revolves once around itself, and then just a little bit further, and ends right here at this point. So here, we're going to erase that. I'm going to move, the terminal point is now over here on the right, with the same initial point. So hopefully this is starting to get you a little bit more comfortable with how these things operate, that these parametric curves can sort of copy on top of themselves, and that period changes of my trig functions do induce some sort of a change in what's happening under the surface. Again, if you're ever confused on these things, just draw a table of values. The table of values is a very easy way to figure out what all the points are. But you should eventually get more comfortable to where you don't need the table of values every time. You should be able to recognize, for example, that in this case, sine and cosine, I know I'm going clockwise, and I see that since there's no period shift, it's just going to try to trace out one circle from 0 to 2 pi. But if I restrict my t parameter, then it's only going to trace out a little bit of the curve. So the next sort of type of example I want to take a look at is a reminder to ourselves that different parametrizations can yield the same looking curve, and to remind ourselves why direction matters. So in this example, I'd like to consider the following parametric equations. So the first one is something we've already sort of seen. Here I want my parametric equation, C, to be given by, say, t squared. And here I'm going to let t range between negative infinity and infinity. We saw this one in class yesterday. This is given as the natural parametrization for y equals x squared. So we'll remind ourselves of that. This is the natural parametrization of the function y equals x squared. And so we know what this looks like. This looks very simple. It's this curve right here, and we know that it traces itself out in a left to right fashion. Okay. No problem. This is something that we understand pretty well. But things get a little weird and a little interesting when, for example, we start taking a look at alternate characterizations. So let's take a look at the following parametric equation. This is again C, where the x-coordinate now is sine of t, and the y-coordinate is now sine squared of t. Where here I'm going to ask t to live between 0 and 2 pi. This one's a little more weird. However, what we'll note, and maybe I'll do this in orange, is that if I eliminate the parameter, notice that x is equal to sine of t. So y, which is sine squared of t, is equal to simply x squared. What that means is we're looking at, again, y equals x squared. Well, that's this picture. So actually, instead of using the variable t, using the variable, the sort of quote-unquote variable sine of t is going to produce the same looking curve. But as we took a look at yesterday, just because the Cartesian coordinate equations look the same, just because the sky view of the graph will look the same, does not mean that the parametric equation is the same, because direction and how this curve is traced out is important. Well, let's take a look at it here. I think this is weird enough that we should draw a table of values. So we're going to have our t, our x, and our y. And then we're going to start plotting some points over here on the right. So let's start with a parameter. Here we're going from 0 to 2 pi. Let's start with 0 and see what we get. Sine of 0 is 0, so therefore x and y are 0. Let's go for, say, pi over 2. If we plug that in, sine of pi over 2 is a 1, so therefore we get 1, 1. If I plug in pi, I'm going to again get 0, 0. If I plug in 3 pi over 2, the game changes a little bit. X is going to be my negative 1 because it's sine. Y is that quantity squared, so that's going to be positive 1. And then we get to 2 pi over here, and we're going to again get 0, 0. This is a little bit weird looking. We seem to start at 0, 0. Then in sort of a continuous fluid manner, we go to 1, 1. So this is 1, 1. We end up going up here, like that. And then awkwardly, we come back to 0, 0. So somehow, I'm now coming back to 0, 0, which means I've gone up the curve here, and then I've come back down the curve to 0, 0. Then I go up the curve to negative 1, 1. I go up the curve to negative 1, 1, and then I seem to go back down to 0, 0. This is a really weird looking parametric equation. The curve of it is a little bit like a pendulum. I start at 0, 0, I swing up, I swing all the way back to the left, and then I swing back down to the bottom. So here, this note that the initial, that 0, 0 is the initial and terminal point. But this is a really weird picture. Somehow this starts at 0, 0, swings up to 1, 1, then swings back to 0, 0, up to negative 1, 1, back to 0, 0. Here I really have to write out a full description of what's happening, because if someone were to just walk in and see these weird arrows, and they don't know where the initial point and where the terminal point is, this would be a very confusing picture that we're taking a look at. But from a sky view, this picture and this picture are the same. However, the tracing of the picture, the direction of the path, how many times it overlaps, notice that this curve, interestingly, this curve right here, traces itself twice, right? Because we go up once, down once, up once, down once. We've covered the entire length of this curve twice. So this is a very interesting parametric equation that we can obtain by simply taking the boring natural parametrization of the parabola and then swapping out the base variable for some other function. Of interest is that if I swapped out this period, or this parameter, for say 4 pi, it would just swing multiple times. If I swapped this parameter out, say for 18 pi, it would literally be a pendulum going up and down and up and down and up and down and up over and over and over again. And if you think that this might actually be related to some sort of physics observations of sort of swinging objects, you may be correct in that thought. There are other interesting ways to yield this picture. Let's try, for example, well, no, you know what? Let's actually write down what happens if I extend this forever. I'm going to take this exact situation here, and instead of 0 to 2 pi, let's just actually write that out. Let's go negative infinity to positive infinity. We now have an idea of what's going to happen here. It's going to start at 0, 0. Well, it doesn't even start at 0, 0, right? It starts at all the way at negative infinity, so I'll delete that. And we're not quite sure where that begins, but it's going to be, so we're not quite sure what the initial or terminal point is. So there is no initial / terminal point. But the entire point here is that it is constantly drawing from 1, 1 to 0, 0 to 1, negative 1, 1, back and forth, back and forth, back and forth, back and forth forever. And so this swings back and forth forever. So again, highlighting that if you take the exact same parametric equations, but you change the parameter, you get wildly different conclusions. And if I take the same picture, but I change the parametric equations just slightly, so that each of these have the exact same Cartesian equation, y equals x squared, I also get completely different parametric curves out of it. So there's a lot of subtleties running around in the background here. So I think the last example I'd want to take a look at in this mini conversation is an example of a parametric curve where your test points have to be carefully chosen. So let's take a look here. Example. Consider c of xy, where here the x-coordinate is given by the parametric equation t plus 1 over t, and the y-coordinate is given by t minus 1 over t. And for the sake of argument, let's just go ahead and restrict t to be positive. This is an example of something where you can't even get a feel for what's supposed to be happening here. And in fact, this is an example where eliminating the parameter is deceptively difficult. But I'll show you how it's done. But before we get to that point, let's just plot a table of values. Let's go t, x, y. Well, remember, the whole point is that the x, y become a coordinate, and the t is a parameter. So t has to be greater than 0, so let's make some good choices here. Let's plot some obvious choices, right? Let's plot, say, let's go with 1, let's go with 2, maybe make it a little bit bigger here. Let's go with maybe a 5, and maybe a 10. I'll leave it to you to verify with me that if I plug 1, 2, 5, and 10 into the x and y equations, that I'm going to end up with the following. For 1, I'm going to end up with a 2, 0. For y, t equals 2, I'm going to end up with 5 halves and 3 halves. For 5, it gets a little more interesting. 5, I'm going to get 5 plus a fifth. So that's going to be, 26 over 5. And then we'll get here 24 over 5. And for 10, we're going to end up with, 101 over 10 and 99 over 10. You can convert these into decimals if you'd like to make it easier to graph. But if we do start plotting these, what we'll end up seeing here is we're going to end up getting, t equals 1 gives me, it's a 2, so that's going to give me this point. Then we're going to end up with 5 halves, that's 2.5, and 3 halves, so if that's a 1 and that's a 2, we should end up maybe somewhere here. And for a 5, somewhere all the way out here maybe, we'll be all the way up here. And for a 10, we'll be all the way up here. And so you see, you start connecting the dots, and you get that curve right there. Now, I do encourage you to, of course, arrows. I can't forget that, right? Arrows. So it would seem that this has a nice initial point maybe at 2, and it has no terminal point. And if you left your answer this way, I would completely understand why you left it this way. However, there is a slight problem here. Notice that this t value is greater than 0. However, I never tested values that were very close to 0. For some reason, I only tested values greater than 1. So what I found was that this is the point at t equals 1, t equals 2, t equals 5, t equals 10. But there are a lot of perfectly reasonable numbers between 0 and 1 that I just chose to omit for some reason. The point of this example is don't do that. These are only half the points that we can actually test. If I were to take that and move it down a little bit, there's a bunch of other points that are perfectly valid points to test. What about, say, 1/10? What about, say, 1/5? What about, say, let's go with maybe 2/5? And then we could even sneak up even further if we wanted to and do something like 4/5. And you don't even need to make it that fancy. We could even, maybe you don't like the 5 underneath it, fine. Maybe we pick a 1/4 and a 1/2. Maybe that is a little bit more your speed. Either way, these are perfectly valid parameters for t. If I plug in 1/2, what do I get? 1 over 1/2 is just a 2. So 2 plus a half is 5 halves. That's exactly what I had here. If I plug that in over here, I'm getting 1 over 1/2 is a 2, so I'm getting 1/2 minus 2. That's a negative 3 halves. So I'm getting the exact same point I had. Instead of 1/2, I had a 2 here. So I'm getting the exact same coordinate here, except instead I'm introducing a negative into the y-coordinate. So in that spirit, maybe instead of looking at 1/4, I'll just keep 1/5 and 1/10, because what I see there is that the 1/5 coordinate is going to be the same thing as the 5, 26 over 5, but with now a negative 24 over 5. And 1/10 is going to be, again, 101 over 10, but now a negative 99 over 10. And in the spirit of keeping the same, well, we'll keep it the way it was. So there is another branch to what's happening here. Notice here I'm at 101 and 10. If I did want to convert that, this would be 10.1 and negative 9.9. So if I go all the way out here to 10, then there's a point right here. This is a hollow point at 10 comma negative 10. I'll make that bigger. This is hollow. My curve is not actually allowed to be at t equals 0. But in some sense, this is what happens when quote-unquote t equals 0. But note, I can't actually do that, so that's only in air quotes. And then the whole point is, now I have a whole separate branch of this curve moving from as close as we can to 10, negative 10, and it's moving upward. This branch right here is exactly the branch that's occurring for t greater than 0 and less than or equal to 1. Whereas the blue branch that we had up here is the branch that occurs when t is greater than or equal to 1. And so what we see is that this curve has no real initial point, but not because it's blowing up to infinity, but just because we're not allowed to actually touch that point. And no terminal point because we are blowing up to infinity. And that's maybe a distinction that's worth noting here. So we have no initial point, but it's not infinite. Whereas here, there's no terminal point, and we'll say it is infinite. So a small distinction to be made, but if you don't include these fraction parameters, you end up only getting half the picture, which can lead to only half the information. So I think this is an important example to show off how subtle things can be. If you do recognize this picture is a parabola on its side. Well, you might even be inclined to think it's a parabola on its side. It's actually not a parabola on its side. It's actually what's known as a hyperbola on its side. And so to give you a quick recap on that, a hyperbola is going to be a curve that looks something like this. It's something like x plus a squared minus y plus b squared equals something like a c squared. And the picture for this is always going to be something at, say, this is going to be at, so I guess I should write this as minus. So this is going to be at a comma b. That's the sort of center of my hyperbola. There are going to be two sort of parabolic looking wings on either side of it in an equidistant way. And you might recall, for example, that there's sort of these transversal lines in between them. And this forms some sort of a box that your hyperbola can't touch. If you don't remember a lot of this, that's okay. It's really, we're not going to import a lot of this information. This is from what's known as conic sections, sometimes taught in a pre-calculus class. And the point is that this picture is representing the rightmost branch of a hyperbola. So in spirit, we should be able to take these equations, manipulate them somehow, and make it look like something like this. It turns out that we can do that. Take a look at this. So note here that we have that x is equal to t plus 1 over t, and y is equal to t minus 1 over t. Thus, consider the following computations. On one hand, we know x minus y is equal to, well, it's going to be t plus 1 over t minus t minus 1 over t. So the t's cancel, and I'm going to be left with just a 2 over t. And if I add x plus y, I'm getting t plus 1 over t plus t minus 1 over t. Now the 1 over t's cancel, and I get a 2t. And then conspicuously, if I take the product of the x plus y and the x minus y, I'm going to end up with, on the right, a 2. But in between, I notice, so maybe the correct way to write this is to put this over here on the right. And then on the left, we FOIL, and notice that we're going to get x squared minus y squared. So indeed, what we end up with is we end up with something like x squared minus y squared is equal to a 2, which is exactly this kind of situation, where the sort of center of our hyperbola is at 0, 0, and that's exactly what we have going on here. But what we see is that if I were to just graph this object with the theory of hyperbolas, we would be at 0, 0. I'd go out to, notice here we went out to 2. It's no surprise because there's a 2 right here. So we go out to a 2, and then we'd have a branch over here on the right. We'd also have at -2 a branch over here on the left. So if I were to just eliminate the parameter, which by the way, this is a completely non-trivial way of eliminating the parameter. I think very few people would think that this is an obvious way to do this. But if you did manage to pull that off and you got this sort of Cartesian representation, you would graph this picture. But this picture is not the picture in question. The picture in question is just the right branch, specifically one starting at 10, -10 and going off to infinity. So this is an ineffective way of determining what the parametric curve should look like, because the whole point is that this curve, the actual curve in the example, starts down here, goes all the way up here, and only traces out that branch. This is when the parameter t is greater than 0. I should note that if I did change the game, and if I did allow, say, t is less than 0, that would have traced out a branch sitting over here instead. So that would have been on this side. So this is a really sort of complicated example that I wanted to work through so you could see some sort of the highlights of the nuances going on in the background. It might be worth noting that if I did want to get this curve, this one I highlighted in orange here, so we'll say this, if I wanted the right branch given as the highlighted in orange bit, I could use the following options for parametric equations. We could go with cxy is equal to the square root of 4 plus t squared and t for t between -infinity and infinity. I could have used c of xy equal to 2 secant of t, 2 tan of t, where here t is explicitly between pi over 2 and -pi over 2. I could have done other things that are a lot more weird. The point is that parametric equations get a little complicated. These both will give us exactly this branch that we looked at here. These are two very, very different looking parametric equations. So there are subtleties in every single one of these examples, and there's no sort of one-size-fits-all way of handling them. I think that and you feel free to plug in these points and build a table of values and verify that you end up getting this right branch. I encourage you to do so. But the entire point here is that at the end of the day, when looking at a parametric equation, make sure you plot as many table of values as you can. Carefully trace out the path of your parametric curve. Eliminate the parameter where possible, but know that that's only so helpful. It sometimes gives you too much information. And remember that at the end of the day, your initial point or terminal point, or lack thereof, are important in determining direction. And as we saw earlier here, it's also important in making sure that you understand how often your curve traces over itself. Because sometimes it traces over itself once, sometimes twice, sometimes an infinite number of times. And as we move forward in this conversation, examples like sine and cosine with changed periods or changed domains and what these look like, these are going to be the important examples that we're going to need to import and use later on in this chapter when we talk about polar curves. But I think that's it for today. I think we talked about a lot of really interesting examples, and we talked about a lot of mathematics we maybe haven't seen in a while. So I'll leave you off here. Take a look at some of the homework problems that have been assigned. If you have any questions, of course, feel free to email me or come visit me in my office. I'm always happy to help. Otherwise, good luck, everyone, and I will catch you all later.